Hello, my name is Alex Tunstall, and as Martin said, I work with the Mordor team at RELX, and I'm here to talk to you about running GHC on RISC-V. Oh yes, the lights. So that should be clear. Yes, so as most of you know, GHC is the Glasgow Haskell compiler, and it is needed in order to compile all Haskell software. There are other compilers, but they can't really, the main compiler for compiling Haskell is GHC, and there isn't much else you can do with these other compilers. So we're interested in getting GHC running on RISC-V. So your first question might be, what is RISC-V? Well, RISC-V is what we call an instruction set architecture, or ISA for short, which describes at a very low level the instructions, registers, memory, and I/O operations that a processor supports. So for example, it would say that if we encode these specific bytes into the file, when the processor reads those bytes, it will then do this specific thing. By the way, if you get lost throughout the talk, please do interrupt me and ask. You can raise a hand, and I will answer your question. Because most of the talk builds on knowledge introduced earlier in the talk. So, for example, we have x86-64, which is the architecture running in most of our laptops, desktops, and servers. Or we have AArch64, more accurately known as ARMv8, which is running in all of our smaller embedded processors, such as your routers, your microcomputers, and most importantly, your mobile phones. Most of those will be running ARM or AArch64. So why should we care about RISC-V? Well, one of the big disadvantages with x86 and ARM is that you only have one or two vendors to choose from. In ARM's case, there's only ARM. And in x86's case, you're choosing between Intel and AMD. In RISC-V, since the ISA is completely open for anyone to implement, this means you can have more vendors, so more competition, and better for all of the users of the architecture. On top of that, the architecture isn't designed to work with a specific type of processor. So this means that you can have some very high performance server tier processors which will have hundreds of cores and be capable of processing large amounts of data very efficiently. Or you can have your small embedded processors which you might find in your routers. And RISC-V can handle both of these very elegantly. And for those two reasons, RISC-V has been very fast growing. It was only about 4 years ago that the base instruction set was ratified, and we already have some actual physical hardware available for consumers to buy to use. At the moment, it's still very bare bones, but I will be showing you later some Haskell programs running on the RISC-V system. So when I say ISA, I'm actually talking about a whole family of ISAs. So RISC-V has 4 base instruction sets, 32-bit variants and 64-bit variants. And then on top of these, if we want extra functionality, we can also add in some extensions to get multiplication, vector operations, and anything else we might be interested in. Now, in terms of general purpose computation, we're more interested in what's called RV64GC. And if you remember the other slide, you may have noticed that G wasn't listed there, and that's because it's actually short for this big monster of extensions. So we've got the base instruction set RV64I, that's 64-bit instructions. Then we've got integer multiplication and division, atomics, single precision floating points, double precision floating points, compressed instructions, and the last two you don't need to worry about because only the Linux kernel needs to deal with those. And also anything that does dynamic code generation. So why is it so difficult to get GHC on RISC-V? Why can't we just grab GHC up and just this? Why does this not work? Well, GHC up tells us, I don't know what this is. And this is because RISC-V has completely different instructions. You can't just take an x86 binary, toss it on a RISC-V system, run it. And what will happen if you try that is the system will just blow up, metaphorically. If you're running a kernel, most of the time it will stop you. It will say, hey, hang on a minute, that's not RISC-V. I'm not going to let you run that because it could have some disastrous consequences. All right, so let's try something else. Let's try Nix packages. Now, Nix packages might work for this because it can build from source, and it doesn't. Nix packages does not know how to bootstrap GHC on RISC-V. It can do x86, ARM, and any other architecture that GHC publishes bin binaries for. Well, let's look at the official binaries then. Maybe they've just forgotten to add them in there. Nope, they haven't. There's no RISC-V in that list. As you can see, we've got x86 and ARM. And there are actually a few more that I haven't included in this slide because it would make the list far too long. And as far as I'm aware, no one here has ever used PowerPC. So let's get the sources and compile it ourselves then. So GHC has this wonderful wiki page describing how to compile GHC. I think this one is actually for the old build system, but most of it still applies today. There's this line in it, which tells us that in order to build GHC, we need GHC. So what are we going to do here? The answer is cross-compilation. So we have GHC on x86, we want GHC on RISC-V. Maybe there is some way of getting GHC on x86 to output RISC-V instructions instead of outputting x86 instructions. So that's what we're going to try to do here. And a small note on this point, other distributions, specifically Debian, have already successfully done exactly this. So if you go into the Debian repositories and you search GHC, you will find that they have a RISC-V binary there. So I don't know whether they used cross-compilation, but I'd be very surprised if they did anything else. Okay, so the core idea is that we use our GHC on x86, compile to RISC-V, and then we transfer it to the RISC-V system, and we can run it. So for this, we need something called a cross-compiler, which is a compiler that doesn't target its current architecture, the architecture it's running on, but rather that targets a different architecture and produces binaries that won't run on the current machine. So let's talk about terminology, because otherwise things are going to get very confusing very quickly. We have two platforms that we're concerned with. The build platform, which defines where we're going to be building the application. In our case, this is going to be x86. And we have the host platform, where we're going to be running or hosting the application. This is going to be RISC-V. So actually, there's a third platform that I need to mention here, because GHC is inspired, I assume, from GCC in its design, and both of these compilers can only output code for one platform at a time, meaning if you have a GHC or GCC build that targets x86, you can't tell it I want you to output RISC-V, you need to rebuild a different compiler specifically for targeting RISC-V. So for that purpose, we have the target platform, which says when this compiler is run, this is the architecture it will output. All right, so let's look at an example. Simple Hello World C program, hopefully correct. Let's try and cross-compile this from x86 to RISC-V. So this is what we're going to try and do, a build plan. So the columns represent the programs we're going to be building. We want to build our Hello World on x86 and run it on RISC-V, so I've already filled in that column. And the target platform here doesn't really make sense because Hello World isn't a compiler. So what do we need for GCC? Well, since Hello is built on x86, we need GCC to run on x86, so that's going to be our host platform for GCC. And we need our Hello World program to run on RISC-V, so we need the target platform for GCC to be RISC-V. So we can fill those in. And the GCC compiler we can already get from all our package managers has build, host, and target set to x86. So we're going to need to add an extra step in order to get our GCC cross-compiler targeting RISC-V. All right, so now let's suppose we don't just want to build Hello World, we want to build GCC itself so that we can then build whatever we like on our RISC-V system without having to build it on an x86 system first. So let's swap out Yes, I've filled in the extra columns. Previously, these extra cells did not matter, but we can fill them in with x86 since that's what we have. And so if we swap out Hello World for GCC, you can see that by compiling GCC twice, first we build the cross-compiler, and then we use the cross-compiler to compile GCC for RISC-V, we get a version of GCC that runs on RISC-V and targets RISC-V. So we can then transfer this over to our RISC-V system, and it will run, and it will output code that will also run on RISC-V. And the build platform there is x86, but this doesn't really matter when you're actually running the program. So now let's talk about how GHC handles cross-compilation. Fortunately for us, GHC does support this. Otherwise, we'd be quite stuck. So this is generally how you cross-compile things. We run the configure script and tell it we want the host platform to be RISC-V and we want the target platform to be RISC-V. And GHC chokes on this. So GHC here is complaining about the fact that we've set build and host to different platforms. Because of the way GHC's build system is designed, it expects those two platforms to be the same. And as a result, we get an early error. Fortunately, they actually added a case for this to warn the user rather than letting them go through all the build steps and ending up with a mysterious failure. So let's take a quick look at how GHC does cross-compilation. So you can find a table very similar to this one already on the GHC wiki. There is a page about cross-compilation if you need further details. But in essence, the boot compiler is the compiler you start with. Stage 1 is the first GHC compiler that that the build system will try and build. And then stage 2 is the second compiler that the build system will try and build using stage 1 instead of using the boot GHC. And so for boot, we've got build, 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 meaning that boot is built on build, runs on build, and targets build. This is a compiler we can already get on x86 through our package manager or through GHC up. Then we've got stage 1, which builds on build, runs on build. That's a bit strange, but since build equals host, this is fine. And then targets build. So stage 1 is going to be a cross-compiler. And finally, we have stage 2, which is built on build and runs on target instead of host and targets target. So what this means is that if we do a stage 2 build saying we want to, our host platform is x86 and our target platform is RISC-V, we are going to get a binary that runs on RISC-V and targets RISC-V. So this will do what we want, but GHC has unfortunately confused here the host and target platforms, since that second row of stage 2 should be host and not target. And we can actually see this in the error message here. It recommends to cross-compile GHC itself, set target, and then stage 1 will be the cross-compiler, and stage 2 will be cross-compiled GHC. So hopefully that's clear for everyone. So let's try following the recommendation. We do this, and it works. Fantastic. And now we can write a simple hello world program and try compiling it. And at this point, GHC gives us a segmentation fault. So it's at this point that I need to talk about how the different ways GHC can run. Now, unfortunately, I don't have a slide prepared for this, but there are 3 ways that GHC can generate code. The first one is the native code generator, where GHC will use its knowledge of both the architecture's registers and the architecture's instruction set in order to generate the code for the architecture without having to pass off to another program like GCC. The second one, which it will use if there is no native code generator, as is the case here with RISC-V, is to use LLVM, where GHC will use its knowledge of the platform's registers to generate LLVM code and then compile that LLVM code into the machine code that we want as an output. And finally, the third method, when GHC doesn't even know the platform's registers, is using the C backend, where GHC will generate portable C code, and then it will pass it on to a compiler, to a suitable compiler, such as, in our case, GCC. And when you're compiling your GHC, you can compile it in 2 modes. You can compile a registerized version, where GHC will compile in the piece of code that says these are the registers for these platforms. And this allows you to use the native code generator and the LLVM code generator. Or you can do an unregisterized build, where you tell GHC, I want you to use the C compiler always. And the problem we have here is that since 9.2, GHC has registerized support for RISC-V. And unfortunately for us, this might be the thing that's segfaulting here. So let's try an unregisterized build and see what happens. So as you can see, I've added here the enable unregisterized flag, which tells GHC to do so. If you try compiling on an architecture that doesn't support registerization, then GHC will automatically do this for you. But in this case, we need to do it explicitly. So let's try our test program, and this time it works. So there seems to be a bug somewhere in GHC's register definitions for RISC-V. So moving on, we've cross-compiled GHC, but unfortunately it isn't quite good enough. We're missing quite a few things. We're missing Hadoop, we're missing the ability to use template Haskell, and in general, a cross-compiling GHC should sort of be a last resort just to get a new platform working. So we compile GHC 1 extra time, this time a native compilation using the GHC that we cross-compiled from x86. So now we're running everything on the RISC-V system, and Well, we configure it. We don't need to add in any of the flags for the cross-compilation because we're not doing cross-compilation anymore. We're running everything on RISC-V. And after about 30 hours on this system, it's not the fastest, but some early hardware, we get an output and we can use it to compile our Hello World program, and we get the segmentation fault again. So let's try the unregisterized trick again. So we build unregisterized, and this time it works. I haven't included the output in the slides this time. All right, so demo time. So first of all, I can show you the working GHC. So you can see I've got a Hello World there. Let's open it up. And this is just your regular Hello World. I'm sure you're all familiar with this. And, oh yes, just to show you that this is running on RISC-V, you can see RISC-V 64 there. And we've got some LS CPU output, 4-core system. It's a good start, but it's not much. So let's take a look at what version of GHC we've got here. So I have compiled and prepared GHC 9.2.8 for this, but I've also successfully compiled 9.4.5 and 9.6.2. So just to show you that this is the natively compiled GHC, we can see here we've got build platform, host platform, and target platform. These are all set to RISC-V 64, meaning that this was effectively any trace of the x86 compiler that I used to achieve this has completely disappeared. So let's try compiling Hello World and yes, now it should be clear. So you can see, if I just scroll it up, our Hello World program works fine. And unfortunately, the registerized native build for 9.6.2, in my experience, can actually do this successfully as well. It didn't segfault, even though when I tried doing something more complex with it, it did segfault. So I've also prepared another demo, just to convince you that we can handle more complex software. Has anyone heard of Pandoc? So yep, a few hands in the crowd. So Pandoc is a tool for converting one document file format to another format. So I've prepared here, oh, I forgot to delete that.
Could you do this at the top of the screen?
Yeah, even better, I can put this terminal there, and that should work. A bit of a hack, but okay. So we can take a look at this Markdown document I've prepared, and if I don't corrupt the document and open a terminal, I can try converting this. So this has run fine, and now let's open the file, and as you can see, Pandoc is working fine.
Can you prove this was not prepared in advance?
If anyone has any ideas, feel free to come and take a look. But in fact, if you'd like, you can write whatever Haskell program you'd like on my system and try compiling it yourself if you really want to be convinced. So that concludes the demo. So what are the conclusions for all this? Well, we've got a few issues here and there, but thanks to this exploration... Oh, sorry, Mats, do you have a question?
Yeah, maybe could even do later, but I know that at least some ARM builds, Android at least, they have trouble dealing with template Haskell, and you already mentioned a little bit of template Haskell.
Right, this question is about template Haskell. Unfortunately, I'm not sure whether the unregisterized compiler supports template Haskell. I would need to try that to answer your question. But my guess is probably going to be no, unfortunately.
So does this mean that Pandoc is template Haskell free?
Entirely possibly yes. Although, in order to build it with the unregisterized compiler, I did need to disable quite a lot of test suites, because a lot of test suites seem to depend on either having a multi-threaded RTS, which unregisterized doesn't support, or having template Haskell. Yes, so the conclusion. So I did most of this using Nix packages. It has been a great help, and I have also created a pull request to Nix packages to work with the maintainers to ensure that anyone else can use Nix packages to cross-compile GHC for their platform of choice. So unfortunately, this isn't merged yet. I'm still working with them on it. But you can already check out the code yourself and do some cross-compilation if you're interested in doing that. The second thing is, this approach I've applied to RISC-V here, but it will actually work with every architecture you like. You could even use this to cross-compile from x86 to ARM if you want, if you don't trust the ARM binaries for some reason. So the summary of what we did was, first we cross-compiled GHC from x86 to RISC-V, then we copied our RISC-V GHC to our RISC-V system, and finally we recompiled GHC using the cross-compiled version in order to get a native GHC. So what is missing? Well, first of all, we need to fix cross-compilation with Hadrian. I haven't mentioned this earlier, but the configure error that shows up when you try setting host to RISC-V64, that has unfortunately survived into Hadrian, and the build instructions for cross-compiling GHC will only work with the make-based system, which is now deprecated as of 9.6. And to make things worse, Hadrian no longer confuses the host and target platforms. So when you tell it, give me stage 2 with host x86, it will do that. So this needs to be addressed, because at the moment it's completely impossible to cross-compile any version beyond GHC 9.6. The second thing is fixing the registerized seg faults on RISC-V 64. Third thing is a native code generator, which I've heard 2, possibly even more people are already working on. And finally, once all of that is done and a few releases have passed to let it stabilize, there will be some official GHC binaries so that RISC-V can enjoy the same level of support as x86 and ARM do today. So I think that concludes my talk. Yes, questions?
Yeah. So you have now 9.2 compiled there, and you started the talk with that you can use the lower version to compile larger version. So
Yes, the question is about using an older version of GHC to compile a newer version of GHC on RISC-V.
Yeah.
And to an extent, I have tried that. Unfortunately, it's a bit tricky around the make deprecation, because you cannot build GHC 9.2 or 9.4 using make and using GHC 9.2 or 9.4. In fact, I'm not even sure you can use 9.0. You have to go all the way back to 8.10 in order to compile 9.4. And then you need to compile 9.6. And since each compilation takes about 30 hours, I unfortunately haven't had the time to do so. Second question?
What is the... I understand that there's not much cross-compiling support in Cabal. What can you say about that?
Fortunately, I was mostly able to avoid Cabal because I only tried cross-compiling GHC. I didn't try cross-compiling anything else. And I haven't tried using the GHC cross-compiler with Cabal, but with the appropriate sandboxing and file path hacking in place, I don't really see why it wouldn't work. My only concern there is going to be the setup.hs script, which might cause issues.
Just on the same topic, I'm really curious how Cabal plays to this cross-compilation, because it's just a library and an executable. They are trying to be really low on the dependencies, or not too many dependencies there. So it should be easily compilable, hopefully even without the intended Haskell there. And at that point, you aren't using Cabal to cross-compile anything, you're just using Cabal as an executable. So
I am not myself aware of the problems. I think that it may be like there's no Cabal flag for enabling cross-compilation.
So you can use Cabal to cross-compile my random Pandoc application to work on risv-v from the x86.
Exactly.
Yes.
And there may be deeper issues that make it more complicated than just that.
Yes.
Any other questions? All right, let's end it there then.
This was, I don't know, super exciting. Hopefully it was the same for everyone, but thank you.